stationary points. So last lesson we talked about increasing and decreasing functions, when a function increases, when it decreases. And the first step to doing that was finding critical points. Well, in this lesson we're going to talk about all about those critical points, what they are, and what their importance is. And we're just going to do a couple ways. We're going to do it based on mathematics, and we're going to do it based on the graph of f prime of x. This is actually in the next video, so we'll cross that out. So, if you remember how we got our critical points, we set the derivative equal to 0. Now, it was equal to 0 or undefined. Today we're only going to focus on set equal to 0 part. Undefined is not going to be what we call a stationary point. So a stationary point is only when the derivative equals 0. Now remember, critical points, derivative equals 0 or undefined. Stationary is just where it's equal to 0. So we're going to focus on those. So here's our graph of f of x, a basic f of x graph. Right? And then remember how we figured out where the derivative equals 0? It's all the tangent lines. So here, horizontal tangent line, and here. Now, the point of a stationary point is if the derivative equals 0, it's either going to be a local max, a local min, or a stationary inflection. We'll talk about that more in a second. That's it. Those are your options. So when the derivative equals 0, you have three options: local max, local min, or stationary inflection. So let's talk a little bit more about them. So first, let's talk about this graph in general, right? So we have this thing. A global minimum is the absolute lowest value of the graph, the absolute lowest y value. So global min, remember, we're talking about min, maximum, we're talking about the y values. Will be right here, global min. It's the lowest point on the graph. Likewise, the global max is the highest point on the graph. Now, I'll talk about this in a bit, but not all graphs have a global max and min. Some graphs go on forever, so they have no max or no min. And our local max, local min are these points, right? Local max, and local min. Notice how local max and local mins have they have that like shape like this or like that, and it's when the derivative equals 0. Local max, local min. And now just keep in mind, not like I said earlier, not all graphs have a local max or min. If I give you a graph like this, a global max is the highest point of the graph. This has no highest point. When I say highest point, I mean like, oh, the max should be 10 or 15. This doesn't have that. It's infinity. It keeps on going. So no max, no global max. Right? There's no one highest point. No global max or min. There's still the relative ones right here. But there's no one highest point or one lowest point. Now sometimes the global max and min could also be the local min. If I give you a parabola, this has no max, right? No global max. But it does have a local max, which is also the local min, the global min. So in that case, it's both. Okay, let's talk about a stationary inflection. So stationary inflection, just want to think of the execute graph, right? If you know that graph, it kind of goes like it's right here. Goes up, then it kind of levels out for a second and goes up again. Anytime your graph does that, we call that a stationary inflection. So we'll say it right here is a stationary inflection. Right, so same idea if it's going down and it goes down again. So it's going down and then it goes down again. Like after a brief pause where there could be a horizontal tangent line. That's called a stationary inflection. So you have three options: max, local min, or stationary inflection. Let's see how that works on a graph. Right, so this is my graph as one of each. There's a local max, there's a local min, and there's a stationary inflection. Now let's see what happens with the sign chart. Right, so this is my sign chart. Right, so that's my local max, that'll be a 0. And then before that, if you see it's increasing, so it's a plus, and then after it's a minus. So you're increasing, then you're decreasing. So on the sign chart, it goes from plus to minus. So when you go from positive to negative, it's a local max. When you have a minimum, if you'll notice, it's going down then up, right? You're going decreasing then increasing. So you go from negative to positive, so you're going down then up. That's local minimum. Stationary inflections when it doesn't change, right? Look at it's going up, then it's going up again. Plus plus, right? It's going up and then up again. Stationary inflection. So those are three options. Those are three options you could have, and that's how they happen. Local max when it increases and then decreases. Local min when it decreases and increases. Stationary inflection when it does not change signs. right? Same thing would happen here. It would be decreasing and then decreasing. So it doesn't change signs, stationary inflection. That's what this chart's about. That's what the first derivative test is. It's all about, positive, not positive, negative, local max, negative, positive, local min. And here's the helpful chart I use. Right, so the main idea is it's a local max, right? So first you have to find your critical points minus the undefined ones, just set the derivative equal to 0, right? That's how you always find a maximum, by the way. You set the derivative equal to 0. And then if you do a sign chart and it goes from positive to negative, it's a max. It's a local max. If it goes from negative to positive, it's a local min. If the sign doesn't change at all, then you go up, then up, stationary inflection, down, then down, stationary inflection. So that's the general idea. So now let's talk about a process to actually find them and just do some examples. Right, so first, that's how we're going to get through this. The general idea is it's exactly the same we did last time, right? Finding increasing and decreasing functions. We're just going to add an extra step of, now we're going to look at the critical points, right? If it changes from positive to negative, max, blah, 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 blah. Right, that's all it is. We're doing the exact same thing we did last time, but now we're adding an extra step. So here, right? Step 1, find all the critical points. Set the derivative equals 0, undefined. Right, to find both of them. Then we're gonna make a sign chart, and then we're gonna find, right, in our sign chart we'll do test points. We're gonna find out where it's increasing, decreasing. Because when we do that, we'll do a little sign chart, right? We'll find increasing and decreasing. If it's something like this, it'll be like, oh, plus to minus, that's a max. So like we talked about earlier, if it goes from a negative to a positive, it's a local min. At x equals c, or so we'll talk about this in general, but if they just want the x values, all you gotta do is say the x values. X equals whatever. If they say they want a point, you actually gotta find the point. That's me highlighting the point. So that's if they want the point. Now, if you have the x value, remember how we get the y value? As always, we plug it into the original function. Plug into f of x. Again, notice, right, if I'm doing my sign chart's always, you plug it in, when you do a sign chart, you always plug into that derivative. If it's a sign chart for f prime of x, plug in f prime. If you're doing a sign chart for f double prime, plug in double prime. But if you want a point, the point is on the original function. So we always plug it into the original function if you want a point. And again, if you go positive, negative, like I did up here, it's a max. And if the sign doesn't change, it's going to be a local stationary inflection. And I said, as I just mentioned, the question says find the x values. All you have to find is the x value. That's it. Find out, you're done. If it says it wants to find a local min or max, you got to plug it back into the original function to find it. So let's do an example. This is find all critical points. Let's change that a bit. Let's find all stationary points of this. So if I'm going to find stationary points, we got to find first we got to set the derivative equal to 0 and undefined. So I'll take my derivative, 3x squared minus 27. We're going to set equal to 0. Let's just solve this. Add the 27 over. Divide by 3. 9 equals x squared. Square root it. X equals plus and minus 3. Right? So now let's do my sign chart. And as always, now normally I would do my intervals here because we're trying to find increasing and decreasing. But in this case, I only want to find the critical point. So I'm just gonna do a sign. I'm not gonna bother with the intervals right now because we're not gonna need it. The key is to find the min and max in this case. So pick a test point like -4, point in between here 0, and over here like 4. Again, you can plug it into anything you want right here. So I'll plug 3, -4 squared minus 27. Remember, you always do the square part first. That's 16. 16 times 3 is 48. And that's going to be a positive value. If I plug in 0, I get 0 squared minus 27. That's definitely going to be 0 minus 27, so a negative value. And if you plug in 4, well, again, right, if you plug in 4, it's like plugging -4. Because you square it, it goes away, it's going to be a plus. So now I want to know if it's a min or max, right? So at -3 here, it goes from positive to negative. That's a max. At 3, it goes from negative to positive. So that's a min. Right, so my local min is at x equals 3. Now in this case though, it didn't say find the x values, it said find the stationary points. So I actually got to plug it in, right? So again, if my x is 3, if I actually want the point, it's 3. The y value comes from plugging into the original function. So you have to put 3 cubed minus 27 times 3 minus 20. 3 cubed is 27. That is 81 minus 20. So I get 27 minus 101. That's going to be 70 plus 4. So negative 74. Right, not the most fun thing in the world, but has to be done. So 3 and negative 74 is where my local min is at. That's going to be helpful because in the next video, or in the coming video, we're going to talk about how to actually graph all this. And we're just going to be plotting points and connecting them. Right, so that's my local min. My local max is at x equals negative 3. Same idea, plug it in. Right, because I actually got to find the y value. So if I plug in negative 3 cubed, minus 27 times negative 3 minus 20. This is a negative 81, right? Odd power keeps the sign. 2 negatives make a positive, so positive, 27. So it's positive 81, and then minus 20. So negative 27 plus 61, that's 30, 30, 34. So 34. Right? It makes sense. Local min has a low y value, local max has a high y value. And that's the idea for local max and min. It's a general consensus. Let's do another example. Okay, in this one, let's just say let's find the x values, right? So let's find the x values of critical points. So we don't have to plug it back in, because I assume you guys get the idea. So in this case, again, as always, got to find let's take the derivative. So bring it down, I get x squared minus 2x plus 1. Set equal to 0. Now again, this has to be a factor. That's how you solve it with the quadratic. And that's x minus 1 times x minus 1. So I just get x equals 1, right? Split it up, get the same answer twice. So I only have one critical point. Or sorry. So plug that in. So there's my sign chart. Again, normally I would do the intervals negative infinity to 1, 1 to infinity, but in this case we're only talking about what type of point this is. That's all I care about right now. A test point like 0, a test point like 2. Plug it into your derivative. So 0 squared minus 2 times 0 plus 1, I get 1, which is positive. Plug in 2. 2 squared minus 2 times 2 plus 1, I'm going to get 1. Positive again. In this case, right, again, positive and then positive. If sign did not change, that's a stationary inflection at x equals 1. And actually, if I want to plug it in, it wouldn't be that bad. A little bit of fractions, but let's say stationary inflection at x equals 1. So that's the general idea of how to find our stationary points. Let's do a couple more quick examples to make sure we get that. To more about focus on the calculus. So let's a little review of calculus and see how it goes. This one right here. Analyze the critical points of f of x cosine squared x plus sine. Oh, look at trig. Right? Well, first, I gotta take a derivative. And look at this right here. Some of you guys got this wrong on the test. This is cosine x whole thing squared. So that's a chain rule, right? Bring the 2 down. Leave the inside alone. Times by the derivative of the inside, which is negative sine. I almost messed that up. Derivative of sine is cosine. So let me write that a little nicer while we set equal to 0. So it's going to be negative 2 sine x cosine x plus cosine. How would I solve this? Right? Go to trig. I would factor out the cosine. They both have one. So factor it out. Cosine x, negative 2 sine x plus 1. And then I'll split it. So cosine x equals 0. Negative 2 sine x plus 1 equals 0. Right, solve each one separately. This one I'd subtract 1, divide by 2. If I do that, to negative 2 equals negative 1, divided by negative 2. Sine x is going to equal 1/2. Right, and then again, I don't care how you solve this. You could do the chart, you could do the triangle, any way you want to do it. The key thing to all those is that if you're solving this, you gotta remember all students take calculus. We are doing sine, so remember the way this works, A is for all. And then all the rest of them, it's the sign, it's a plus sign for the one you're talking about. In this case, I'm talking about sine, so that's a plus sign. It makes these two negative. My answer is a positive though, so I'm gonna put it here and here. Right? If you're doing the chart, then once you have that, you just gotta look back and figure out what angle it is and put it on both of these, and then figure out what the answer is. For me, that's gonna be I'll do a triangle 1/2, SOHCAHTOA, opposite of hypotenuse. 1, 2. I know that's automatically a 30-degree triangle. 30 and 30. If you're using degrees, that'll be 30. This will be 180. Then you're 30 short, so 150. Now notice they have in radians. IB actually gives you credit for both ways. So they'll give you credit for putting 30 in 150, even though they say radians. But in radians, this would be pi over 6, so 30 is pi over 6. This would be 6 over 6 minus 1, so 5 pi over 6. Over here, cosine 0. Right, it's a little bit tougher because cosine 0 is not a triangle. 0, 1 are special. It's one of these points here. Now it only wants me to go between 0 and pi, so I'm not going to go all the way around. So here's 0, here's pi over 2, here's pi. This is 1, 0, 0, 1, negative 1, 0. Sine e, cosine x, so it's where x is 0, which is pi over 2. Right, look at all that match, like, ooh, done. You kind of just started. A question is find the critical points, right? Analyze critical points. Is that a max? Is that a min? These are just my critical points. I gotta do a sine chart. Right, so pi over 6 is the smallest one. You can tell by the graph, right? It's over here. The middle will be pi over 2. Then it'll be 5 pi over 6. Right, you pick a test point. Now without a calculus, it's a little tougher. Over here, I'll probably pick something like 0. In between these two, it's a little tough. I'll put pi over 3 or pi over 4. Right, it's bigger than that, but smaller than that. Over here, same idea, put like 3 pi over 4. And over here, I'll probably just put pi. Plug that into there, or to there, and then get the sine chart. I'll skip that for your sake, but that's all it is, this trig, right? You can't forget about trig. It never goes away. Let's look at another one. The interesting about this one is that they give you a domain here. All your answers will be from 0 to pi. If you want to know, if you're curious why that is look at natural log, right? The domain of natural log is only 0 to infinity. So that's why it's like that. Right? If you graph natural log, it looks like this. So negative values make no sense. Right? Don't forget natural log of 0 is undefined. Anything less than natural log of any negative number is undefined. And natural log of 1 is 0. So this is like the derivative of this. So that's how we find that's how we analyze our critical points. Right? So take the derivative, set equals 0, or undefined, find my critical points, but take the derivative. So derivative of natural log is flip it, times by derivative of the inside. And derivative of that is negative 1. So now I'm going to set equal to 0. Right now, before I start, keep in mind, right, if we want to find our critical points, or is where derivative equals 0, or is undefined. Already, I'm going to have undefined. Right, I can't divide by 0. So x equals 0 is where it's undefined. Now I could solve it to find out where it actually equals 0. So add 1 on both sides. 1 equals 1 over x. Let's do a little cross multiplication. Or multiply both sides by x. And x equals 1. Right, so I have two critical points I got to worry about. This one where it was undefined, and this one where it actually equals 0. So then we do this. Here's 0. Here's 1. Again, normally I do my little intervals. But in this case, we only want to care about how to characterize critical points. So like pick test points, negative 1, 0.5, and 2. And like I actually said earlier, this makes no sense. I can have a negative 1. And look at my domain. 0 doesn't count either. So actually, it's only be 1, and something less than like 1/2, and something above it like 2. Right? I don't have to worry about 0 because it's not a domain, and I can't be negative anyway. It's not a domain. So this is actually my sine chart. That's wrong. Right? And the same thing as we always do. Plug this into the derivative, which is this right here. It's not that bad. I'll do it. 1 over 1/2 minus 1. Now remember, this is kind of a trick. anytime you have something like this, like a complex fraction, this is 1 divided by 1/2, which is just 1 times the reciprocal, right? So the short answer is the very bottom thing goes to the top. That's a shortcut. That thing goes to the top. So 2 minus 1 is 1, so it's positive. 2, so let's say over here, right? 1 over 2 minus 1. Well, 1/2 minus 1 is negative 1/2, so that's a negative. Look what's going on. You went positive and then negative. You have a local max at x equals 1. Now, I didn't say x value, it said point, so I got to plug it back in, right? So if I actually want the point, or you always plug it into the original function. So if I'm plugging it back in, let's change the color real quick. I'll plug that into my original function if you want the actual point. If you're doing a sine chart, you plug into its derivative. But if you want the point on the graph, original function, it's going to be natural log of 1 minus 1. Natural log of 1 is always 0. Natural log or log of 1 is always 0. 0 minus 1 is negative 1. So that's where the point's actually at. 1, negative 1. A few more problems. So let's look at this one. This one's a little different. So it's like your favorite, right? F of x equals x cubed plus ax plus b. There's variables in here we got to find. There's values in here we got to find. They're not variables or constants. So this has a stationary point at negative 2, 3. So let's talk about what that means. So that's the key to this whole problem. A stationary point at negative 2, 3. Remember the way we find our stationary points? You take a derivative and set equal to 0 or undefined. Right, but when I do that, right, I'm looking for x. So all I care about here is the x value. What this tells me is when I plug that into my derivative, it equals 0. That's the key to this problem. Right, what's the stationary point? That's the 0 of my graph. So when I plug the x value into my derivative, it equals 0. And what does the point itself tell me? Well, that point itself tells me when I plug in negative 2 into the function, it gets 3. Right, so a couple things there, right? The fact that it's a point tells me when I plug it in for my x, I'm going to get my y. The fact that it's a stationary point tells me when I take a derivative and I plug it in, it equals 0. That's what a stationary point is, right? It's like a max and min point. It's a critical point. So let's do that. We can set up both of them. Right, set up the first one. Plug in negative 2. It should equal 3. So 3 is an equal negative 2 cubed plus a times negative 2 plus b. I can simplify it a little bit. 3 equals negative 8. Remember, odd power keeps the sign. Minus 2a plus b. Add the 8 over, I get 11 equals negative 2a plus b. Right, can't go any further there. That's where I max out. Now let's look at the derivative one. Let's do this one, right? Take a derivative of that. So f prime of x. Bring the 3 down, subtract 1 off. Plus, remember, derivative of this is just a. And that has no x at all, so this goes away. So that's my derivative. Let's do that, right? When I plug in negative 2, it equals 0 because it's a stationary point. So when I plug in negative 2, it equals 0. So 3 times negative 2 squared plus a. Always do this first. 3 times 4 plus a equals 0. Looks like this is going to be 12, and then you subtract it over. Negative 12 equals a. Right? And once you get that, plug it in, find your b. Negative 11 times negative 11 equals negative 2 times negative 12 plus b. 11 equals 24 plus b. Subtract that, b is going to equal negative 13. So there's my a and b. Right? It's all about what that means, right? If I give you a point, that always means when you plug it into the original function, it's an equal to y value. If I say it's a stationary point or a max or a min, that just means that when you plug in a negative 2, when you plug in the x value, it's an equal to 0. That's the key to that. Okay, last thing we're talking about, as always, what if I give you the graph? If I give you the derivative, right? So let's say we give you the derivative function. How do you tell where the max and min happens and whether it's a max and min? Right? It's all about context, right? Remember, if this is a derivative, how do you find derivative? You said the derivative equals 0, right? That's your critical points. So let's look at that first. So here's my critical point right here, negative 1, and right here at 3. Those are my critical points. Now, is it a max or min? Remember the way that works, right? If you go from positive to negative, it's a max. If you go from negative to positive, it's a min. If it doesn't switch, then it's a stationary inflection. So how do I tell from here? Well, look at the graph. It went from positive to a negative. That right there is a max. So it's the local max. Then look at 3. You went from a negative value to a positive value. So, local min. It went down and up. If you like it better, you can also do this on a sign chart, right? -1, 3, and then look at plus, minus, plus, and it works the same way. So that's the general idea. Let's do another one to make sure we got this. All right, so let's look at this one. Right, first, again, this is a derivative. Keep that in mind. It's a lot different. The original function is a derivative. So you go first with my critical points. Critical points is where the derivative equals 0. So, or undefined. In this case, it's only 0. So there, there, and there. Right? X equals -2. X equals 1. X equals 3. All right, look at -2. It goes from positive to positive stationary inflection. Right? It went positive and then positive. So that's a stationary inflection. Look at 1. Plus to minus. So it went up and then down. That's a max. And then 3 goes from negative to positive, and that's a min. Okay, if you prefer, you can always have done like make yourself look at a little sign chart and just look at the graph. Oh, okay, it's on the positive side, and then it's on the positive side, then it's on the negative side, then it's on the positive. Right? And then the same idea. Whatever works best for you. Okay, one last thing. What if I give a second derivative of the graph, right? What is that going to tell me? Well, remember the second derivative? If it equals 0, it's an inflection point. But only if there's a sign change. Right? If there's not a sign change, it's not an inflection point. Right, so look at this. Same idea, right? We'll find our critical points. What are our key points here? It's the exact same graph we just did, I know. But it's a second derivative now, so it's different. Right, key points with these. Right, so x equals -2, x equals 1, and x equals 3. Now remember, this is a second derivative, right? So second derivative tells me inflection point, but that's only when there's a sign change. Look at -2. Plus to plus, no sign change, not an inflection point. Right, there's no sign change because no sign change. Look at x equals 1. It went from negative to positive. Sorry, it went positive to negative. Right? I don't care how it goes with inflection points. It's the fact that it switches signs at all. It means that it's an inflection point, right? It's an inflection point. That's all I care about. Right? X equals 3, same idea. Minus the positive, it's also an inflection point. Right? So second derivative tells you inflection points. First derivative tells you min and max in stationary inflections. And that's kind of the idea of the whole video.